Hello everyone. So in this lecture, I'm going to explain the capacitated plant location model. First, I will briefly go through the setup of the model, the information we need, the decision variable, and then the formation of the equations. And then we're going to solve it in Excel, right? So here we are following an example from the Chopra and Mendel book on supply chain management. From the chapter 5, we'll be going through the example of the company called SunOil. Okay, and SunOil, it's a petrochemical manufacturer which has plants in different parts of the world, so they have business worldwide. So here we can see some data. Here we can see that the company has supply regions in 5 parts of the world, and then they have demand also in 5 regions of the world. Okay, and then we see the demand information for each of the region. Okay, so for example, here the demand for Africa is 7 million units. Okay, so here we see in the box here the information that relates to production and transportation cost per 100,000 units, per 1 million units. Okay, so all these values are actually in thousands. So here it means $81,000 for transporting 1 million unit from North America to North America. This one here means $115,000 for transporting 1 unit from North America to Africa, and so on. Okay, so the demand values are in million and the cost values are in $1,000. Here we also see we have 2 types of plant. One is high capacity and one is low capacity. So the low capacity plants, they have about 10 million units capacity, and the high capacity plants have about 20 million units of capacity. We see the cost of having high capacity plants open is less than double of the low cost capacity. So for example, if I want to have 2 low cost capacity open for North America, then normally it would cost us like $12,000. But if we open a high capacity plant, then it will cost us $9,000 with the same capacity, right? But now here, let's say as a supply chain manager, what you're going to do is you are going to optimize the distribution of the product from your supply locations to your demand locations, and you want to optimize this based on the lowest cost that could be possible. Okay, so we are going to find out how many units to send from North America to other parts of the world, how many from South America to other parts of the world, and so on, right? So, and what will be the optimum minimum cost. So that's what we are going to find out. So for a problem like this, normally our input variables are going to be the number of potential locations and capacity. So in this case, we have actually 5 potential locations, but here we have like high and low, so we can actually consider 10 total plant locations, because we can have up to 10 options. Okay, then for demand points, we have 5 fixed demand points. And the annual market demand, we have here these numbers here, so these are given. So here we see this notation of J, right? So here one idea of reading this table could be that the supply locations, we can call them I, and the demand locations, we can call them J. Okay, and the value of J can be up to 1, 2, 5. And the value of I can be up to 1, 2. In terms of location, it could be 5, but because we can have high and low capacity, then it could be actually up to 10, right? So here, when we say D, let's say when we say D5, then we will refer to the demand of Africa. When we say D3, then we would refer to the demand of Europe, and so on. So it's just one way of simplifying how we refer to all the demand location. Okay, Similarly, for supply regions, when we'll say, for example, here we see like KI, here we say potential capacity of plant I. Okay, so let's say here it could be that when we say KI, K1, then it could mean the potential capacity of North America, low capacity. Okay, when we say K2, it could mean that potential capacity of North America. Actually, we can read it in different ways. So for example, yeah, it's up to us how, in this case, it's up to us how we want to read this. Do we want to go low and high, and then for the another plant low and high, or do we want to go like, for example, say K1 is North America low, K2 is South America low, K3 is Europe low capacity, K4 is Asia low capacity, K5 is Africa low capacity, and then we start from 6, we start with the high capacity one. So 6 would be the North America high, 7 would be South America high, and so on. Okay, so this is how we could read this. Okay, then here, if I is annualized fixed cost of keeping plant I open. So here we have this fixed cost. Okay, so this will be the cost for keeping a plant open, fixed cost for keeping a plant open in each of the locations, right? And then the CIJ. So here CIJ would mean the cost of producing and shipping one unit from plant I to market J. The cost includes production, inventory, transportation, and tariffs. In this case, we put everything in this cost. Okay. So here, so when we say CIJ, so let's say the value of CI is 1 and J is 1. So C11, that would mean this value. Okay. From North America to North America, because this is our 1, 2, 3, 4, 5, and then again, so on. So let's say then when we say C53, then the value would mean this one, 103, from Africa to Europe, okay, and so on. So that's how we can read all these values in the table, okay. So these are the information that are kind of inputs to the model. We have to start with this information, okay. Sometimes when we are working in a real life case, we will not have a table like this, and then we have to estimate this information, okay. We have to figure out a way of coming to this estimation. We can assume this information, we can search. So for example, for plant locations, it's up to the company how many plants they want to have. For demand locations, it's also up to the company how many markets they want to serve. And then for identifying the demand in each of the location, we have to do some kind of demand forecasting or judgmental forecasting to come up with some values of demand for the product, right? And then again, capacity depends on the company, like how much capacity the company wants to build in each of the plants, right? And then for the costs, the number of plants will have some fixed costs for building and equipment. So there will be some cost associated with that. And then for moving goods from each of the locations to the demand locations, and we will have the CIJ, the cost of moving and inventory and transportation and tariffs and so on, right? But in a problem like this, what we are going to do is actually, we are going to find out which plants to keep open or close, and how many to deliver from each of the supply locations to each of the demand locations. So usually in any optimization problem, we can solve with 3 things. We always need 3 things. One is these decision variables, then we need objective function, and then we need constraints. Okay, so here we are using yi to define whether our plants are going to be open or closed. And here we see the yi can take value of 1 if the plant is open and 0 otherwise. So we are using binary variable. Okay, so when we use this binary setup here, and with the normal linear programming approach, okay, then it becomes mixed integer linear programming. Sometimes you will see words like MILP, so mixed integer linear programming models. So this is actually a mixed integer linear programming model, a simple one, but it's a mixed integer linear programming model. Okay, So then in the objective function, normally what we want to do is we want to define if we're going to minimize cost or maximize profit. Okay. So in this case, we are going to minimize cost. So now let's say here, if I multiplied with yi, this part gives us the variable cost of having, gives us the fixed cost of having each of the plants open or close. Okay. So it refers to this cost. So for example, here, yi, when the value of yi is 1, so let's say if I refer to y1, okay, if I refer to y1, and if the value of that is 1, so that would mean North America, value of North America is 1. North America could be y1, okay? And then the cost of North America, that is 6,000, that will be multiplied with 1, okay? And then if we find out with optimization that the value of y1 is 0, then 6,000 will be multiplied with zeros, and then the value will become 0, and there will be no cost accounted for this plant in our model. Okay, and so on. Okay, so and then this part here, it gives us the cost of producing and delivering to from one supply locations to the demand locations. So for example, here what it means is that, so we will take sum of all the cost multiplied with corresponding volume that will transport from each location, supply locations to the demand locations. For example, if I try to break it down, let's say C11 will be multiplied with X11. Okay, then we will have a plus C12 will be multiplied with X12 plus C13 will be multiplied with X13 and so on. Okay. So the value of X that we don't know yet, that we will find out actually based on the optimization. But for now, we know the value of cost because that we already found out and put it in our table. So here, for example, C13 is this value, the cost for North America to Europe. Okay. So when we will find out the value of North America to Europe, how much we are going to send, that will be simply multiplied with this cost and then add up for all the cost multiplied with the values. Okay. Here we have 3 constraints. A simple way actually to look at it would be that the first one is a demand constraint. Second one is a supply constraint. And here this is a to indicate this binary constraint, whether plant is open or not. And here this we can call non-negative constraint. Okay. So now in simple words, when we are working in supply chain, normally the demand we will have, our supply locations have to meet this demand. Okay. So that's the simple idea. The demand we have, our supply, all the supplies to the demand location has to be met. So for example, if I try to draw it here somewhere here, so let's say this is one of my supply locations, another one, 5 supply locations. Okay, I call it S1, 2, 3, 4. And then we have these demand locations. Let's say again, I just put 5 dots, demand locations. Okay. So now let's say the demand here can be supplied from all the supply locations, all the 5, right? Each of the demand locations can get supplies from all the 5 supply locations, right? So here we are saying that, the demand of, let's say D1, the demand of D1 has to be met by all the supply it will get. So for example, it will get from X, the value, the supply from here, S1 to D1, we will call it X11. From here to here, it will be X21. So here we will say X11 plus X21 plus X31 plus x41 plus x51. Okay, so this is for one. This equation represents this one figure that I have drawn here. But then for the demand location 2, it will be the same, right? So then we will have to write something like this, that D2 will be equal to x11 plus x21 plus x31 plus x41 plus x51. Okay, and so on. Similarly, we will have 5 equations. But then writing these 5 equations can be time consuming and it's a lot of space. So instead, we can just write dj, where the value of j is 1 to 5, should be equal to xij, summation of xij. Okay, and where I equals to 1, so the first supply location up to the end supply location. Okay, all the supply locations. Okay, so this is how we write our demand constraint. Okay, great. Now, so the main idea here was that every demand location has to be met. All the demand has to be met in every location from all our supply locations. That is the simple idea here. Then we have this supply constraint. So normally in supply constraint, the idea is that all the supplies that we are sending from one location, it cannot exceed the capacity of that location. Okay, so let's say if I pick a different color here, and if I try to draw it, so if I try to draw it here, let's say we have these 5 supply locations. Okay, we have these 5 supply locations, and then we have these 5 demand locations, right? These 5 demand locations. Now, each location can serve all the 5 demand locations, right? If I give it the name D, each supply location can serve to all the demand locations, right? So here it is x1, 2, x1, 3, x14, x15, x1, one, 1, 1, 2, 1, 3, 1, 4, x15, right? So here the supply we are going to send from this supply location to all the demand location cannot exceed the capacity of this supply location. Okay, so let's say if I kind of want to write it down, that would be like x12 plus x13 plus x14 plus x15. I missed x11. This has to be less than or equal to the capacity of this plant supply, plant 1, K1 multiplied with whether it's open or not. Okay. Similarly, we can write 5 equations for the 5. So K1, 2, 3, 4, 5. Okay, so we can write 5 equations like that. Okay, so for example, the equation for the 5th one would be like x51 plus x52 plus x53 plus x54 plus x55 should be less than equal to K5 and Y5. So instead of writing the 5 equations one by one, we can just write that Xij should be less than equal to Ki Yi, where the value of K could be 1 to M, because M indicates where the value of K could be 1 to N, where the value of K could be 1 to N actually, because N is the number of capacity. So the value of it could be K 1, 2, 3, 4, 5. And here actually it could be up to 10 because we have 10, we have 5 low capacity and 5 high capacity, right? And then we just take a summation here. And here we say J equals to 1 up to M. Okay. So the demand going to one of the demand locations to the 5 demand location, going from X, going from each of the supply locations. So that's what we have here, supply and demand. And here we are just saying that the value of yi, this one, it has to be the 0 or 1. Either our plant will be open or closed, binary. And here we are saying that the value of xij, the delivery values, how much we will be delivering from one location to the another location. This cannot be a negative value. It has to be the 0 or positive value. Okay. So that's actually the formation of our mixed integer linear programming model for a capacitated plant location. So here now I explained all the equations and the inputs and the decision variables. But now I'm going to show the solution using Excel in the next video.